So let's resume the talk. Now let's look at the specific part of the Spark called runtime, the task memory management. So why is memory an issue when we are running tasks? One fact is that Spark tasks run in a shared memory environment. There is no hard constraint that prevents a task from using up all the memories available. Thus, the memory contention can be severe. Also, we have witnessed more and more workloads that are trying to catch data in the memory to cut down I/O time that also bring more pressure to the task memory. Thus, we often face the problem that the memory resource is not enough. Spark memory usage can be roughly divided into 4 major categories. The execution memory, like shuffle and aggregation buffers. The storage memory, like cache data. The user memory, like memory buffer for allocated large sparse matrix. And the reserved memory, which is reserved for Java itself. So let's introduce them and see how to tune Spark memory usage in the following. Execution memory is the memory used to buffer intermediate results. For instance, if you are doing a sort operation, you have to catch all the input data from upstream and sort them locally and let the downstream operators consume the result. So through the description, we can see the execution memory are normally short-lived. Once the data has been consumed, it's safe to free them. The storage memory is for reused data for future computation. For example, some cached RDD. So you only need to recompute them for later computations. The cached data can be long-lived until they are explicitly released by the user. We use a LRU eviction approach to spill data to release the storage memory, which means we always evict the least recently used data. Thus ensure we can keep the hottest data still in the storage memory, and the time consumption of fetching them can be as low as possible. Spark uses the unified memory manager for memory management on executors. The unified memory manager expresses execution and storage memory as one single unified region. All memory requests can be fulfilled until the whole memory region is full. Then it keeps acquiring execution memory and evict storage memory as you need more execution memory to continue processing data. Spark uses the config spark.memory.fraction to set aside memory for internal metadata, user data structures, and imprecise size estimation in the case of sparse on usually large records. Another 300 MB memory is reserved, even for small heaps, to avoid out-of-memory error. Spark uses the config spark.memory.storage fraction to determine the amount of storage memory immune to eviction, expressed as a fraction of the size of the region set assigned by Spark memory.fraction. The higher this is, the less working memory it may be available to execution, and tasks may spill to disk more often. We can control the fraction of execution memory and the storage memory by the config spark.memory.storage fraction. We use a dynamic occupancy mechanism to manage the memory usage, which means if either execution memory or storage memory is insufficient, but the other is free, then it will borrow the other's space. But if both parties don't have enough space, it will always evict storage memory, because the spilled execution data will be sure always be read back later, while it's not always the same case for the cached data. The config spark.memory.storage fraction ensures the fraction of storage memory is no less than a baseline in case of insufficient memories. But this doesn't resolve our problem at many scenarios. The memory resource can be still not enough because we really have tasks that do memory-consuming operations. We really have the need for more memory. So Spark introduced off-heap memory to help elevate our memory management ability. The reason why not directly increase JVM memory is that we want to get rid of the GC burden. So the off-heap memory can be enabled by the config spark.memory.offheap.enabled, and the memory size is controlled by spark.memory.offheap.size. It can be divided into execution memory and storage memory. The off-heap memory directly acquires memory from the operation system, so it bypasses the JVM. The speed of accessing off-heap memory is roughly the same as that of on-heap memory, so it's a lot faster than from disk. The advantage is it's not bound by Java GC, so no stop-the-word issue. The disadvantage is you have to manually manage your memory allocation and memory release. But it also gives us a chance to save up some memory when dealing with some Spark internal data storage issue. The first way to reduce memory consumption is to avoid the Java feature that add overhead, such as pointer-based data structure and wrapped object. There are several ways to do this. The first is to design your data structure to prefer arrays of objects and primitive types instead of the standard Java or Scala collection classes. Because the common collection classes such as Java hash map and linked list, they use linked data structure where there is a wrapper object for each entry, and this object not only has a header, but also pointers. Usually, it will use up 8 bytes to the next object in the list. The second is to avoid the nested structure with a lot of small objects and pointers when possible. So the next structure is not ideal because each distinct Java object has an object header, which is about 16 bytes and contains information such as a pointer to its class. So for an object with very little data in it, this can be bigger than the data itself. The third is to consider using numeric IDs or enumeration object instead of strings for keys. So Java strings have about 14 bytes of overhead over the raw string data, since they are stored in an array of chars and keep the extra data such as the string length. And strings store each character as 2 bytes due to the string actually supports UDF 16 encoding, so it is using up more memory than actually needed in many cases. Thus, 10-character string can easily consume 60 bytes. These all make our memory pressure more severe. So a few tips to tune the memory config in Spark. To make better use of Spark memory, here are some tips for modifying the memory-related configs. So you may increase the value of spark.memory.fraction to be able to expose more execution and storage memory. The default value is 0.6. So it would be safe to increase this if you are confident about your application usage scenarios and ensure that it's safe to do that. The disadvantage is the application may face higher risk of out-of-memory exception because the lack of memory reservation. So if you are reading a large sparse matrix, then it is possible that it will book up all the memory reservation and throw a OM exception. So this is one thing that was to be noticed. So the other is that you may increase the value of Spark memory, the storage fraction, to be able to expose more storage memory. Thus, user can cache data more aggressively. The disadvantage is that this may also lead to less execution memory. So the execution memory is fully booked. We may observe task spill to appear more often. You may enable the use of off-heap memory by set Spark.memory the off-heap.enable to true. So the off-heap memory size is decided by Spark.memory the off-heap size. Off-heap memory can be used as the execution memory as well as storage memory, and is not bounded by GC. The only thing to remember is user have to ensure that the on-heap memory and the off-heap memory together must fit in total executor memory. Otherwise, the executor memory is not enough, and if you are writing the off memory, it may got over the boundary. So yeah, you may also increase the shuffle file buffer size by increase the value of config spark.shuffle.file buffer and the Spark unsafe sort spill reader buffer size. Higher shuffle file buffer can help optimize the disk I/O and thus reduce I/O time. But it also means more execution memory consumption. So if the execution memory is not sufficient, then the task spill may happen more frequently. That will also hurt the performance. So you need to evaluate the trade-off of that. Yeah, so that's all for the Spark task memory. And I will hand the rest time to my colleague Chris for the PySpark and the vectorized readers. Thank you.
So hello, everyone. Thank you for coming to this talk. I'm Chris Mock, and I'm a software engineer here at Databricks, and I'm mostly working on Spark SQL. So I used to work on various JVM implementations, and I am a OpenJDK committer. So today, I'm actually filling in for my teammate, Takuya Ueshin, who prepared the contents, but couldn't make it to the summit due to some issues. So kudos to Takuya for preparing this. So Xingbo has covered the Spark core side of the runtime implementation, and now let's switch gears and look at a few specific areas on the Spark SQL side of the runtime. So first, let's look at vectorized readers, because it's sort of like an oddball in the Spark SQL runtime execution. So one of the things about the Spark SQL runtime is that it's mostly a row-based execution engine, which means you process one row at a time. But there are some file formats that are already optimized for read performance, and they're stored in columnar formats. So if you eagerly convert these columnar formats into a row-based format for Spark to consume, then you might slow down the read performance. So what do we do here? The easiest way to do it is to read in the columnar data as is, and then let the Spark execution engine down the stream to use an adapter to read from these columnar format as if it's a row, but it's actually just reading multiple columns in lockstep, so you get a conceptual row, but the data is actually still stored in a columnar format. So these vectorized readers, because you can do read in batches, and because it fits the original file format, the performance can be much, much better than the ones that are not vectorized. So in this case, the performance can be 9 times faster than the non-vectorized version. So currently, Apache Spark has built-in support for vectorized readers for the Parquet format and the ORC format. More support for other file formats are coming on the way. So as a side note, the arrow format is used for exchanging data between the JVM executor and the Python workers. So there's an opportunity for doing vectorized readers there as well. And we'll be touching on PySpark in a bit. So in the future, if new data sources wish to support vectorized readers, the data source v2 API is a good place to start. It exposes Spark's internal columnar batch API so that readers that wish to pass columnar data into Spark SQL can do that easily without any tricks. The data source v2 API is still evolving, but it'll be generally available in Spark 3.0. I won't be diving too deep into the data source v2 API itself, but you can keep track of what's going on in that Jira ticket. So to make a plug for the new Delta Lake project that we've just open sourced, it sits on top of Parquet, so it also takes advantage of vectorized readers. And then it's got a lot of cool features that are listed here. Like all of them are really important if you want to do really scalable and then reliable operations, especially in the cloud. Cool, so next let's take a look at how functions are implemented in Spark SQL. So what's behind what looks like a function call, right? Like if you write full X, what's behind that? So what looks like a function call can actually be a lot of different things. So I've listed a few examples here. You can have built-in functions that are scalar. You can have aggregate functions. You can have window functions, generator, and then some of the variants of user-defined functions like the scalar user-defined function, the aggregate user-defined function, and you can also have some newer cool features like higher order function, and some oddballs like range, which is a table value function. And they're all different. So just to note that generator and table value functions both produce more than a row. But they're subtly different because, so for range, you're actually producing a whole table. But for generator, you're basically generating something and then joining with the original table. So they're subtly different. But I won't be diving too deep into these two. We'll be covering some of the other functions. So let's take a look at a few different aspects for all these functions to help us understand how they're different from each other. The first aspect is scope, which means how much context you need to see in the table for you to run this function. As you can see, most functions only take the context of a single row, so you don't need anything else from your surrounding rows or like the first row or the last row. But aggregate function and window functions may need either the entire table or may need a window of it. So that's one thing to note. And then the second is what I would categorize as data feed, which is like, what do you feed into the implementation of the function? So most of these just take in other expressions as input. But Python UDFs and other non-Java, non-JVM UDFs actually take in a batch of data at a time, and then it's implementation specific about like how to feed this batch into the actual function. So for instance, Python UDF might just be feeding a row at a time from this batch, but then Pandas UDF we'll be covering later actually feeds a whole batch into the UDF implementation. And that's something to note as well. So by virtue of feeding in a whole batch, that again is going to take more than a row from the input. And so why do we do this special handling for non-Java UDFs? That moves us to the third point, which is the process model. So most processing of these functions are implemented in either Java or Scala or some JVM language. So they can be easily run in the same JVM as the executor. But Python UDFs and other language bindings are actually run in external processes. So for example, here we use a Python worker process to run the Python UDF. And in order to reduce the inter-process communication, we need to make sure that we design a bulk interface instead of a chatty interactive interface. So that's why we send data through the wire in batches. So of all these aspects above, when you see a function implementation that requires input data from multiple rows, for more than a row, or if they produce multiple rows like generator and table value functions, then they need to be implemented on the level of a physical operator. Otherwise, if they only need the context of a single row, they can be easily implemented with just calculus expressions. So that's, this is the means. And last but not least, there's a really important distinction between the user-defined features and the built-in features. The built-in features are trusted by Spark SQL, so they use the internal types directly. So for instance, primitive types are all the same among internal and external. But if you're talking about more complex data types like strings, the internal type for string would be the UTF-8 string inside of Spark SQL, and the external type would be a Java lang string. So the internal data type is what we use directly in execution, so that's really fast. And it's usually more compact than the Java counterpart. But the external API is more stable, and then it interops with existing libraries on the outside much better, with the caveat that there's more overhead. When you run it, you need to convert between the internal and the external representations. Cool, so with that in mind, let's take a look at what kind of UDF support we have in Spark SQL. So we have our built-in support for Java and Scala UDFs that are Spark SQL specific. And to interop with Hive, we also support running Hive UDFs. And then there's also Python and Pandas UDFs and other language bindings that we'll be covering later. So there are two major categories of JVM-based UDFs. And the first is Scalar, which we just call user-defined function. And the second is user-defined aggregate function. And its properties are mentioned in the previous slide. Because it needs to take in more than a row, you need to implement more than one function to fulfill its requirements. So for instance, here are the four main functions that you need to implement in order to have a full UDAF implementation. So initialize is when you want to initialize the aggregate buffer. Update is when you take in input from rows and then do the aggregation and then put the data into the aggregation buffer. Merge is when you do a final aggregation. You need to merge two aggregation buffers into one. That's when you use this function. And evaluate is when you take the aggregation buffer and you evaluate it to the final value of the aggregate function. So Hive UDFs are enabled are available when you enable Hive support. And it's actually not that different from the Spark SQL counterparts. It's just different in the sense of how you register it. So in Spark SQL, we have wrappers for each of these Hive UDFs. So here's the bit about the overhead. So before we invoke a user-defined function, we have to convert data from the internal data format to the external data format so that these UDFs, which are not supposed to see the internal data types, can work well. So this is actually pretty similar to how typed dataset operations are implemented. For typed dataset operations, you also have this encoding and decoding step. But over there, you use what's called the encoder support. And here we just do a less fancy version of that. In the future, we may migrate the encoder support into UDF execution as well, so that you have a more covering support when you run UDFs. I know a lot of people may be really frustrated when they want to pass, let's say, nested case classes for UDFs, and you just can't do it because you don't have encoder support here. So once you've converted the internal data type into the external data type, you then invoke the UDF. And it's just really simple. You just invoke it. And then like for Java and Scala UDFs, because it runs in the same process, invoking a UDF is just a simple act of invoking a normal method. And after the invocation, you convert the return value back to the internal data type. Cool. So with that in mind, let's take a look at the PySpark API as an example of how languages outside of JVM are integrated into Spark SQL. So PySpark is a set of Python bindings for the Spark API. And notably, it provides the RDD API support and data frame API support. And that's the foundation of all the other libraries that are based on the RDD or data frame APIs. So for example, MLlib and structured streaming. And built into Spark SQL is that we also have support for Spark R, which is the R counterpart. So a little bit about the difference between RDD and the data frame API support in PySpark is that in RDD, you're calling the RDD API so that the RDD API itself provides the backbone of your query, but the actual content of what you want to do within each operation is supplied in a Python function, in a Python lambda. And so whenever you need to run each row of the RDD, you really have to call back into the Python worker process to run it, which can be really slow. But with data frames, if you're only using the built-in support and not using any of the Python UDFs or Pandas UDFs, then the whole query actually stays in the Executor JVM. You're just building the query with the data frame API, so it's not different from Java or Scala accessing the data frame API at all. So that's the nice part of it, and like when you're just using the data frame API, you'll actually have the same level of performance regardless of you're using PySpark or Scala. So how do we run this thing? Now, this is getting back to the runtime aspect of it. So Python scripts, you run it on the driver side. And on the driver side, there's an external Python process that actually runs your Python script. And it sends these requests to the Java side of the driver. And the Java side of the driver builds up the query, forms the DAGs, and then sends those DAGs, as what Xingbo covered, to the executors for execution. And then on the execution side, you have your normal JVM executors. And these talk to external Python workers for running Python UDFs and then the callbacks to the PySpark RDD. So for ease of interop, we can actually convert between PySpark data frame and Pandas data frame in a bidirectional fashion. And one thing to note is that Spark SQL data frames, and in this case PySpark data frames, usually are lazy. So if you call a transformation on a data frame, it doesn't cause this data frame to execute. It's only when you do a count or when you do a collect or a show, those are actions that will trigger the actual execution. But if you do to Pandas, you may view this as if it's a transformation, but it actually isn't, because you're actually going out of Spark SQL and going into the Pandas land. So you will actually be triggering data frame execution just like collect. But what's different about this is you're collecting data in the arrow format instead of in a pickle format. And the brand new way of doing interop is even better if you are really familiar with Pandas and you just want better performance. So the new Koalas project brings the Pandas API directly on top of Spark SQL, where you can keep using all the tools that you're familiar with, but just get a much better Spark level performance. And as Reno has covered in his keynote, here's the link to the GitHub project. All right, so let's drill down even further down into a specific aspect of the Python and Pandas UDF implementation. So as you can see, the way you declare a normal Python UDF versus a new Pandas UDF is actually really similar. So you must be assuming that these are implemented in a similar fashion, and they are. So the basic infrastructure for implementing Python execution looks like this. The purple square is what's running in the JVM. So you've got upstream physical operator feeding rows to a Python runner, and the Python runner collects these rows into a batch of data, sends it over the wire to the Python worker process, where the data gets deserialized, and you invoke the actual UDF, and return the data in batch back to the JVM side. So what's different? So for normal Python UDF execution, the wire format is actually a group of 1,000 rows or less, packed into an array, and then pickled into the Python pickle format, which is not known for like really high performance. And then once the data arrives on the Python worker side, Python deserializes, unpickles the data, and then runs a Python loop to invoke the Python UDF row by row. And so it's slow in the sense of you're collecting data in the pickle format, and then you're also running a Python loop to invoke the UDF. So in contrast, Pandas UDF runs a similar infrastructure, but instead of collecting the rows from a physical operator upstream into a batch of rows, you collect them into a batch of columns in the arrow format. You send it over the wire, and then you push that into the Pandas UDF, where the whole batch of data goes directly into the Pandas UDF for a columnar execution, which is much faster. So here's a recap of the previous two slides. Now, because of the reduced serialization overhead, and also because of columnar processing on the Python side, Pandas UDFs can be much faster than the old Python UDF. So wherever you can, if the semantic fits, try using the new Pandas UDF for better performance. Typically, you can expect a performance gain of like 3x performance improvement over the old UDF implementation. In some cases, in the exotic case, it can be as fast as 100x or more. So that concludes my portion of the talk. For some of the topics, you can go and read some of the talks from previous Spark Summit. And if you're interested in knowing more about Spark internals through the Spark UI, there's also a talk this afternoon on just how you would dive in from the Spark UI down into all these concepts that we covered in this talk. So thank you.
All right, we have some time for questions. If you would like to ask questions, please come to the the microphone in the middle of the room.
Hey, can you hear me?
Yes.
So the last but one slide where you are talking about the inter-process communication between the approach of transferring the rows versus transferring the batch of columns. The perf gain, what was the crux of the perf gain reason? So basically, is it because of the compression of the payload by a column by column? Is that the reason, or is there something else that because of which performance got influenced?
So thank you for your question. So the question is, what are the areas of perf gain when we use the Python, the Pandas UDF? So it comes from various aspects. And if you're just running the non-grouped Pandas UDFs, then the performance benefits come from using the arrow format as the wire format, which means on the Python side, there's no real like deserialized step because the wire format and the actual in-memory format is the same. So you're sending the same format representation to Python, and then Python can directly use this for execution. And also, when you run this thing, you're not running, like on the Python side, you're not running a Python loop to process the data, but instead you're using pandas to do like a columnar execution on this arrow format directly. So let's say if in pandas UDF, you're running 1,000 iterations on that batch of rows. Here, you're just making one Python invocation into something that's natively optimized, and you're processing 1,000 rows at a time.
Okay, so it is mostly inside the Python shell of execution operation benefit, but not the true compression, decompression cost of the
So
payloads.
the compression part is definitely does play a role, but that's something you can actually configure, like what compression mechanism you want to use over the wire. Yes, arrow format does usually provide a better compression ratio.
Got it. Cool. Thanks.
Thank you.
When would you want to turn the vectorized reader off?
Ah, that's a good
So I
question.
kind of got like screwed by that.
I would say usually you just leave it on, but if you hit any bugs, then you turn the vectorized reader off.
Yeah, that's what happened to me. But I was wondering why that was happening. I just threw an error saying like, oh, blah blah blah, turn vectorized reader off, and then so I turned it off and it was okay. But I don't understand why. Like, it's breaking.
So I'm not really familiar with that, but we can take this question offline,
Sure.
And we can chat later. But my understanding is that the old row by row implementation, like, it's just been out there longer, which means people have been hammering it more. So you fleshed out bugs a little bit more. And then the vectorized reader case, like, because from the Spark point of view, you're not, like, the actual processing is actually not that different. So it's fully inside of the reader. And so let's say if your Parquet library says, oh, I've got a bug in the vectorized path, then that's what you get. Yeah. Thank you.
Hey, I have a question about the UDF you just talked about, specifically for the front arrow and to arrow to UDF you guys open sourced in Spark 2.4. I still find out like it's not very user friendly in terms of like we try to migrate from D stream to structured streaming, but in terms of like a schema evolution, something like it's basically it's unusable. Like in terms of you want to evolve a schema, you want to change it. Like in the structured streaming, it's very like you can't define your self-defined object as your data type. All the data type are supposed to be the built-in enum inside that class. Like, I just wondering, like, what's the best practice for like serialization for structured streaming?
So serialization actually has nothing to do with schema evolution in this case, because like all the serialized data that we're talking about here, these are all like ephemeral, right? Like they're really temporary, transient. And what happens with like you're not holding on to the serialized data for a long time. So as long as your input and the outputs are defined in the right schema, it should just work. So your question is a little bit more about, I guess, the migration story from D streams to structured streaming. We can totally take this offline, and I can hook you up with some of my colleagues that are more familiar with that topic.
Cool, thanks.
Thank you.
Hey, great talk, thanks. I have first question on the Pandas UDF. Is there a limitation to amount of, like what is the scope on the variables that are serialized over wire that the Pandas UDF can actually refer to? Because I've noticed that if it is in the global scope, it actually gets serialized, but if it's in the class scope, it does not. But so I was wondering if there is like a limitation.
I wasn't able to.
If you declare, like, if you're referring to some variables that are globally declared in the global namespace versus those are declared in the class, at the class level, the variables at the class level are not serialized, and you can't refer to them, and it throws like a Spark exception. But like at ones that are the global, they are actually. So is that a limitation? Because it kind of creates a very weird where you want to have the Pandas UDF inside a class, but then you have to kind of do some hacky global programming.
Yeah, that is a limitation. And there are multiple ways you can work around it, but it's going to be pretty convoluted. So let's take this offline.
Should I just contact you directly?
Pardon me?
Okay, I'll take this offline with you.
Yeah.
The second question is that there was in the earlier talk, in the last session, mentioned the use of Spark CPUs and versus the tasks. And it was like by default, it was set to 1, and the task was set to 5, which means each core has one CPU that is allocated. Is there any case where we would want to actually set it to like 2 CPUs and or like the number of executor cores are 5? Like, can you give an example?
Sure, the answer is yes. So the Spark task.cpus is what controls how many conceptual CPUs you want to spend on a single task, right? So let's say if you're doing something really complex, you're doing your own like locally parallel operation within a task. So let's say if you used RDDs, where you have full control over what's in the Lambda, or if you use type data set operations, which again, you have full control over what's in the Lambda, you can actually do your own, like you can spin up new threads inside of it, right? And then you can do parallel processing within a single task at your choice. So in that case, Spark doesn't know about this, and Spark needs you to provide the information about that. So if you tell Spark, hey, I want to set spark.task.cpus to 5, and then on a, or maybe set it to a 4, and then on a single executor node, the physical machine, you have 4 cores. Then you're effectively setting the degree of parallelism on a single executor node to 1, right? Okay. So that tells Spark, hey, on a Spark level, don't have that much parallelism, and I'll be doing my own stuff. And so, so parallelism is one thing, and the other is, let's say if you're doing a really heavy sort operation, and the sort buffer can be really big, and you want to stop it from spilling a lot. You may actually want to reduce the degree of parallelism per node so that your sort buffer doesn't get in the way of like other task execution, and then like multiple tasks like step on each other's toes, and then everybody starts spilling, and you're actually going to run slower. So that's one of the like edge cases where you want to decrease the degree of parallelism and still get a better performance.
Okay. Just last quick point. You had mentioned there is another talk that is happening where the Spark UI internals are going to get covered. What is that talk?
So Xiao, are you still here? So the gentleman was asking about the Spark UI
okay,
talk.
I know. The hydrogen talk. Okay.
The Spark UI talk. What slide is it?
That's the hydrogen talk. Yeah.
Your talk.
Yeah, my talk.
It's this afternoon.
Yeah, this afternoon.
At 3.
3:40.
3:40. Okay.
Okay.
You can get out.
All right. Cool. Thank you.
Get down.
All right.
So, I have a question about the vectorization for the packet reader. So as I know that vectorization may utilize the SIMD instruction in the processor. So how do we ensure that in the Java, how do we ensure the SIMD instruction will take effect? Is there any as I said now, Java don't have intrinsic like C or C++.
Could you repeat? Could you stand a little bit closer to the mic? And because I wasn't able to make out your question.
I mean, how do we ensure the vectorization take effect?
I see.
Because if you use the code is run on the JVM.
So I like to split this question into 2, and the question is, how do you make sure that we're actually doing vectorization when we're using the vectorized readers? So that's a really good question. But so I come from a compiler world where I care more about SIMD vectorization, and I treat like my view of vectorization before coming to Databricks was actually just like SIMD instructions. But that's not really the case in the database world or in the data processing world. Vectorize can mean two things. One is just batch execution. You read in a batch, you process it in batch, and you spit out the result in batch. And the next level is what we think of vectorization as SIMD, right? Yeah. So the vectorized reader that are mentioned here definitely fulfill the first target, which is they definitely read in things in batches. Okay. But in terms of like whether or not you're getting the best performance because you're making the best use out of SIMD instructions on the hardware, that is like, you need to like investigate yourself. Like there are actually pretty easy ways that we can get in touch offline that I can show you how to investigate what the JVM JIT produces as instructions. So you can actually verify for yourself whether or not you're getting the SIMD instructions that you're expecting. Or you can use the Parquet CPP library and then integrate it smartly into Spark to make use of the vectorized
I see. Yeah,
code
okay.
in the C++ version.
Okay, thanks.
You're welcome.
Earlier you mentioned koalas. It's tempting to believe that koalas is this magical thing that just suddenly scales out pandas. But I imagine it's probably not actually that.
So it doesn't scale out pandas. So there's Dask, right, that actually scales out pandas. So koalas is inspired by Dask, but what it actually does is it just shims the pandas API that you know and love, and directly map those operations onto the Spark SQL data frame. So that's basically it. And if you look at the source code, it's really simple. There's not a lot of code in there. Yeah. And if you just go down to Databricks /koalas /frame.py, that contains the backbone of this level of shimming. And so it's pretty easy to understand. Like you can look at how these operations are mapped onto the native operation on the PySpark data frame.
Yeah, I was looking at it last night. Is there plans to implement some of the NumPy functions?
That's a good question. So in the README of that project, you can see that for like feature requests, you can definitely open issues. All right. And I'm sure like NumPy is going to come up a lot because if you have the Pandas API already, like why not support it?
Okay, thanks.
Thank you.
If I've got two UDFs that need to hit a Python worker, does it need to like go back and forth to the JVM twice, or can it stay in Python and like not have to be serialized?
That's a good question. So you're asking about if I have two Python UDFs that are nested, right? Like I had invoked one Python UDF and the result feeds into another Python UDF. Is that right?
Yeah.
So in that case, it actually stays on the Python side. Like we actually collect the set of Python functions that can run in a single go, and we split that out into a single physical operator called batch eval Python, and that's what gets sent over to the Python side for execution.
Thanks.
You're welcome.
Is there any memory limitations of the Pandas UDF? Like if you do UDF on the whole data frame as opposed to doing a group by before using the Pandas UDF?
I'm not sure I understood the question, but if one of the things with grouped Pandas UDF is that there's some extra overhead of doing grouping and then invoking a Python UDF yourself in the old world. Like there is no like grouping support for Python UDF before Pandas UDF. So that adds a lot of overhead, not only for the boilerplate that you need to write, but also at the runtime, there's a lot of execution overhead. And with grouped Pandas UDF, you actually get to have more native implementation that's just better optimized, and then like it invokes Pandas less. And so there's a much better performance there. So the cases where you get like a 100x performance benefit, some of those are like in the grouping world. But in terms of like specific recommendations or not, let's take that offline.
Okay. And any memory limitations in terms of?
Memory limitations. Yeah, again, let's take the full discussion offline.
All right, thank you.
I'm happy to answer any questions offline. Thank you.
Sorry, I have a question on the Arrow support for Spark R. Is it something on the roadmap for the supporting Arrow on Spark R?
Could you repeat the question?
The Arrow support for Spark R, like the
Arrow support for
Spark R.
For Spark
R.
Oh, for Spark R. That is definitely on the roadmap. It's actually coming soon.
Thank you.
Yeah, thank you.
On one of the slides, you had Arrow is used for the intermediate data set for Python, PySpark.
You mean here?
Yeah, that one here. Is there a disadvantage of using having Arrow as the intermediate data set?
Well, not really. I mean, Arrow is pretty good for this purpose. It's actually designed for this purpose. So I'd say it's a much better fit than the original pickle format, at least. So it's columnar, that's good. It compresses better, that's good. And on the Python side, you're actually running that format directly, so that's all good. One of the things with Arrow, with Pandas UDF actually, is not directly related to Arrow, but in Pandas UDF, you're working on data frames or a series. You're not working on individual rows per se, right? So if you have, if you wanted to use some Python functions on some objects, for example, then you can't just, if they expect scalar values, then you can't just pass this pandas series to that function. You have to like figure out a way to do that mapping, and that can become really slow. So like, if all of your operations stay in the pandas world, then it's pretty fast. I don't see any downside.
All right, everyone, let's give Chris, Maryann, and Shambo a big hand.